Okay, good afternoon, everyone, and welcome back. Yeah. So yesterday we talked about sampling distributions. I'm sure we have gone through. So today we're going to start a new topic on estimation of population values. We're actually just going to be looking at confidence intervals. But before we go into confidence intervals, we'll have an introduction on some estimators and types of estimators. Okay, so to begin with, this is lecture 7 from the Notes on our portal, and I'm sure you can download it. So when talking about estimation, we expect that we should be able to distinguish between a point estimate and a confidence interval, as well as constructing confidence intervals for means, proportions, and variances. And now, I think I've already talked about this. Okay, for the mean, we have to know that there's a case when the population variance is known and when the population variance is unknown. So we have two cases. You need to know which formula to use in each case. Yeah. Okay. So an estimator of a population parameter is a random variable that depends on a sample information. So any random variable that depends on sample information is known as an estimator. Now the value of that random variable is what we refer to as an estimate. So you just have to know estimator and an estimate. An estimator will be a random variable and the estimate is the value of the random variable. Okay. Now, we have point estimates and confidence intervals. So we say that an estimate is just the value of an estimator. Now, a point estimate is a single number. Okay. And a confidence interval provides us a range. Okay. So which one do you think is easier to use, an estimate or a confidence interval or an interval to estimate your parameter? Which one would you prefer, an estimate or an interval? Anyone? There's a question here. There's no standard answer. You just tell me which one you would prefer to use to estimate your parameter, either a point estimate or a confidence interval.
What's the difference? But
I've just stated the difference. I said you're both, if you're trying to estimate the mean, you can have one value, okay, to estimate your mean, and that is a point estimate, okay? So then you can also have a confidence interval for the mean, okay? So you have a range. So you may decide to estimate your population mean using the sample mean. So your sample mean becomes the estimate, the point estimate. Okay, but if you estimate your population mean using a confidence interval, even that same interval will still estimate what? Your mean. Now I'm asking which. Okay, so someone is saying it depends on how accurate you want your information. An interval is less accurate than a point estimate. Perfect. Yeah. So actually, this can still be his opinion. It makes sense, I think, to us. What are others saying? Which one would you prefer to use? A point estimate or an interval? to estimate your population mean. Okay, people are typing. Yes, yes. Okay, I didn't expect raising of your hand. Yeah, you can just go on. Uh-huh. We can get what you're saying. There's nothing. There's nothing.
You're muted.
Oh, okay.
I think point estimate because it's more accurate when giving the answer.
Okay. Yeah.
Yes.
Okay, that makes sense. Some people are typing, want to hear your views. Or others with different opinion. Okay. All right. We can move on. So it depends with what you want to achieve. Okay. Sometimes you want to know the exact mean. Okay. So if you want to know the exact mean, you might want to use a point estimate. You just get values from the sample and you estimate your population mean using the sample mean. So in that case, you're using your point estimate, which is the sample mean, to estimate your population mean. Okay, but you can also construct a confidence interval, which gives you a range of values. And sometimes you may want to make a decision based on maybe the lowest and the highest, based on some limits or some intervals. Okay, you have a range, then you would go for a confidence interval. So we are all, in this case, in all these cases, we're trying to estimate the population mean or your population parameter. Okay. Now we can also use the sample proportion to estimate our population proportion. So in this case, the sample proportion will be our point estimate because it just gives us one value. So when you just get one value, you're obtaining a point estimate. Okay, but if you construct a confidence interval around the sample mean, then you're getting an interval to estimate your population parameter. So we have point estimate and confidence intervals, all used to estimate the population parameter. Okay. So your estimate, okay. So the point estimator is denoted by that theta hat. That's a theta. That's a hat. So it's theta hat. So we're saying that a point estimator can be biased or unbiased. In simple or in day-to-day language, how can you explain a biased estimator and an unbiased estimator? So we're trying to estimate a population parameter, right? Like the mean. What is a biased estimator going to be? Is it going to be equal to the population mean or it will not be equal to the population mean? For a biased estimator, what do you think? So bias is just from the definition of bias, like the normal definition of bias. When something is biased, we're kind of saying it's corrupt. Okay. Like that's the synonym, right? Now, a biased estimator is an estimator which is not equal to the population parameter. Okay. So an unbiased estimator will actually be equal to the population parameter. Okay, so the expected value of the point estimator, if the expected value of the point estimator is equal to the population parameter, then we say that that point estimator is unbiased. But if it is not equal, then we say it is biased. So we're saying that, okay, some noise in the background. The sample mean is an unbiased estimator of the mu, of the population parameter, which is the mean. Now, what did we say the expected value of the, okay, there's some noise. Let me just mute. Okay, what did we say the expected value of the sample mean is? What did we say the expected value of the sample mean is? In the previous lecture, okay, from the sampling distribution, the expected value of the mean of the sampling distribution, what is it? Okay, there's a question. What is the expected value or the mean of the sampling distribution? I'm waiting for your answers. You guys, I'm waiting. We sang about this in the previous lecture. The mean of the sampling, the mean, I mean, the expected value or the mean of the, see now I'm also getting confused. So it's the mean of the sampling distributions. I'm waiting. Okay, just say something. Maybe you don't understand the question or what, because now I don't know how to proceed because I've asked and you guys are all quiet. I can't get what you're saying. I can just unmute your mic. Unmute. Yes.
What's the question, madam?
The question is that
the question isn't clear.
Oh, the question isn't clear. Okay, when we talk about the mean of sampling, of sample means, in the previous lecture, when we were talking about sampling distribution, we talked about sample means, right? Then we said that the mean of sample means is equal to some population parameter. What was that population parameter that the mean of the sample means is equal to? Or maybe it's too easy. Yes? Is someone saying?
No, madam.
You know what, you guys, these topics,
Isn't it the population mean?
That's what I was waiting for.
Using the same previous questions for yesterday.
Pardon?
Using the same previous questions for yesterday.
No, I'm just actually using.
The mean of the sample means is equal to the population mean.
Yes, that's what I was looking for. So these topics are related. You don't have to study, like yesterday we looked at sampling distributions, and then you want to pack everything that you learned on sampling distributions. No, you have to keep all those concepts and try and relate them to the following topics. Like now, we said that the mean of the sample means is equal to the population mean. Now, what can we say about the sample mean? Is it an unbiased estimator or a biased estimator? It's going to be what? Unbiased, because because it is equal to the population parameter. You get it now?
Yes.
Yes.
So the sample mean, again, in the previous lecture, we said that the expected value of the sample variance is equal to the population variance. Okay, so that makes the sample mean an unbiased estimator. Okay, the proportion as well. The proportion is actually equal to, the mean of the proportion is just equal to the population proportion. So that makes the sample proportion to be what? An unbiased estimator. Okay. So what about if we find, if we calculate the mode? Is it always equal to the population mean? We calculate the mode from the sample. Is it always equal to the population mean? It depends, right? Sometimes the mode is equal to the population mean, and sometimes it is not equal to the population mean, right? So we say that the mode is a biased estimator. Okay. So we're just trying to relate what you know to the concept of biasness and, unbiased and biased estimators. Okay, so I hope that was clear. Okay, so I'll go to the next slide. I think now next we just have a graph just showing us unbiasedness. So we have estimator 1, which is theta hat 1. You see it is centered at the population parameter. So we say that theta hat 1 is an unbiased estimator. But when you look at theta 2, it is not centered at the population parameter. So it means that the mean of theta hat 2 is not the population parameter. So that means theta hat 2 is a biased estimator. Okay, there's some noise. So when there's a noise and I suspect a particular mic, I'll just turn it off from here. Okay. So apart from the biasness of an estimator, sometimes we want to know, okay, the slides are taking quite some time. So you can just download the slides as well so that you just have, sometimes it takes long, especially when they are. Okay, so I'll just click there again. Okay, someone is typing. Okay, we can just download the slides so that we. Okay, so we have our slide 9. Okay, so in this slide we can calculate the biasness of an estimator. That is the expected value minus the population parameter. Now we see from this slide that if we have an unbiased estimator, then the biasness of that unbiased estimator will just be 0. Okay, the noise again. Okay. Okay, it's taking some time today. Okay, so we just move. I hope we have already downloaded the slides. Yeah, so that we can just move, because it's taking a bit of time. Okay, so yeah. Okay, so sometimes apart from the vastness of an estimator, we are interested to know if our estimator is efficient or not. Okay, so you may have different estimators, but you want to know the most efficient estimator. So the most efficient estimator will be an estimator with the least variance. Okay, so we say that let theta hat 1 and theta hat 2 be two unbiased estimators based on the same number. So if we have these estimators and they're unbiased, then we say that theta 1 is more efficient than theta 2 if the variance of theta 1 hat is less than the variance of theta hat 2. And the relative efficiency for the estimators is obtained by dividing the variances. So that's on the most efficient estimator. Okay, so again, I'll still just click. It's taking some time. Okay. Okay, so the next slide, in the next slide, we now move to confidence intervals. Now, confidence intervals are very important. I think we established earlier when we were talking about point estimates in the confidence intervals that point estimates are maybe more accurate than interval estimates. But we see here that interval estimates actually provide more information about a population characteristic than a point estimate. So sometimes you want to know more about a population parameter, and you'd rather go for a point estimate. Yeah. Okay, so an example would be okay, if you want to estimate the time at which you have high sales in a store. Okay, if you want to estimate that time, if you use a point estimate, you'd maybe have a time, say you'd get an average, or you find a mean, get an average, and then you find that the time when business is at peak is, let's give an example, say you're carrying out your research in Hungry Lion, and you want to know the time at which business is at the peak, at its peak. So if you get an average of the sales, the time, okay, and find that actually the time at which business is on the peak is 13 hours because it's lunchtime. Okay, so when you do that, you've obtained a point estimate, because maybe you're just finding an average from some sample. Okay, now if you take a confidence interval on the same data, you would find that maybe the time would range from 12 hours to 14 hours. Okay, so that now gives you would have maybe as a manager or as a researcher, you would have to find out the reasons as to why you have that range. Okay, why you have that interval? Okay, maybe you'd say, okay, at 12 hours, other people might be hungry, and other people might have started ordering, and that's why we have a lot of orders coming from around 12 to 14. Okay, so in this example, we're just trying to show that an interval provides more information than a point estimate. Okay, so we call those intervals confidence interval. They give us confidence to some level. Okay, now that level of confidence is what we call the alpha. Okay, actually it's 1 minus alpha. Yeah. So let's get to the next slide. Any questions up to now? No questions? Again, I advise that we download our slides because we're taking long to taking long. Okay, so an interval gives us a range and all that, and say that we construct a confidence interval based on observation from one sample. Then we also state our level of confidence. Note that we never use 100% confidence, okay, when we are creating an interval, okay, because it's just an interval. So we use the levels of confidence to explain our intervals. Okay, it's taking quite some time again. Okay, so the level of confidence is actually 100 is obtained by multiplying 100 and 1 minus alpha. So okay, let's go to the next slide. Okay, so from the next slide, we talks about the confidence level. We're saying that we obtain that through multiplying. Okay, we have our slides. Okay, so that's how we obtain our confidence level. We say 100 multiplied by 1 minus alpha percent. So in a 95% confidence level, what is our alpha? In a 95% confidence level, what is our alpha? In a 95% confidence level, what is our alpha? So answers should just be popping because now we are over 100 in this class. What is our alpha in a 95% confidence level? Yes? What is our alpha? Peter, are you saying something? Because
0.95.
0.95. So what is 1 minus 0.95?
0.05.
1 minus 0.95. Now,
0.05.
you get that 0.05 multiplied by 100. Are you going to get a 95%? You won't. So the alpha, when you say 1 minus alpha multiplied by 100, it should give you 95%. So in this case, it is
So
the opposite. Our alpha is
0.05. It's 0.05.
yes. So our alpha is 0.05. So that when we calculate that, we should have a 95% confidence level. So for a 95% confidence level, our alpha is 0.05. So that we say 1 minus 0.05, we have a 95, 0.95. And multiply that by 100, you have 95%. Okay. So if our alpha is 0.1, if our alpha is 0.1, what is the confidence level?
Ninety percent.
Okay, so that's okay. Yeah. So if our alpha is 0.1, then, okay, so I just typed the question. If our alpha is 0.1, what is the confidence level? That was the question. Okay, so the confidence level is calculated in that manner. Okay. And if our alpha is 0.25, what is our confidence level? 0.25?
75%.
Though I think most of the time we use confidence intervals up to 80. Yeah, because we are creating a range and we don't want a percentage, a confidence level that is too low. So we want a level that is at least 90 something or maybe more than 80. So here what we say, and this is just showing us the process. If we want to estimate the mean, which is unknown, okay. So if the sample mean is, say, you from a sample, you collect a sample and find that the average or the sample mean is actually 50. Okay. Now when you create, this will be your point estimate. When you create a confidence level or interval, you're actually constructing an interval that will maybe say we are confident that the population mean lies between 40 and 60. So in the confidence interval, we have an interval, but the point estimate, we just have one value. Okay. So we move to the next slide. Again, it's taking some time. Okay, so I think maybe we just move to how to construct a confidence interval, the general formula. So the general formula is the next slide. So we have a general formula for constructing a confidence interval. Okay, so in the confidence interval, we use a point estimate, and then we add and subtract the reliability factor multiplied by the standard error. So there's what we call the reliability factor, and you have your standard error. It has to be in this format. Okay, so always your confidence interval has to be in that format. Your reliability factor depends on the desired level of confidence. It also depends on the type of distribution that you're using, whether it's Z, it's a T, yeah, distribution. So we have now the cases, different cases. We have different cases. We first construct a confidence interval for the population mean, the population mean, population proportion, and population variance. Now, you remember that we are using, we don't know the population mean or the population proportion or the population variance. We just want to estimate. That is why we are creating or constructing the confidence intervals. So there are cases when the population variance is known and when the population variance is unknown. Okay, so if the population is known, then we use the Z distribution. So we're saying that if the population variance is known, then the population is actually normally distributed. And if the okay, so I think if the population is known, there are two cases. It's either the population is normally distributed or it is not normal. If it's normally distributed, then of course we go ahead with the Z. But if it's not normally distributed, then remember the central limit theorem. What does it state? Central limit theorem, what does it state? What does the central limit theorem state? Okay, so I've typed the case in. What does the central limit theorem state? Or do we know the central limit theorem? Maybe let's start from there. It's okay, you can just be free. You can say you don't know, I'll still explain. But I just need to know if you know. Okay. So someone is typing, if you have a population with mean, mu, and standard deviation, and take sufficient large samples from the population with replacement, then the distribution samples will be. Emmanuel, what have you done? I think you've just copied this. Emmanuel, this typing was too fast. I know your typing can be very fast, but no. Didn't you just copy and paste in here? Emmanuel, please, we want to hear your voice. You can't cheat while I'm here. Let me look for this slide, actually. Emmanuel. Okay. Okay. Someone else. Okay, so okay, working smart. Okay, okay. I need you to explain in your own words. Please explain in your own words what the central limit theorem states. Now that at least you've seen from that answer from Emmanuel, I need you to just explain it in your own words. Mm-hmm. Yes. Okay, we're waiting for the central limit theorem. Okay, the other people are saying they don't know. Okay, I'm waiting for those that can explain in their own words.
When the sample size increases, the standard error decreases.
Then,
The standard error decreases.
when the sample size increases, the standard error decreases. Okay, that's some kind of just, okay, no, it's not the central limit theorem, but it's a good observation. Okay. So, Stabile, please just explain in your words now. I've seen that what you have typed, and you're saying that the distribution tends to be normal. But you can now just explain. Okay, the larger the sample, the normally distributed they become. Okay. Okay, I think from all the answers, I can see that we are now getting it. I'm sure we now know what the central limit theorem states now. Other people still typing? Okay. So, okay. Yeah, so the central limit theorem just states that if you have a sample larger than or greater than 30, then the distribution of the population would tend to be normal. So you just assume that the population is normal. So in this case, if the sample variance is known, then it's either the population is normal, or if it's not normal, check whether the sample size is greater than 30. Then you assume that the population is coming from a normal distribution. Okay, so that's what those points earlier. Yeah. Okay. So I think I'm saying all that you played to guys. You now understand the central limit theorem. Okay, so in that case, if the population variance is known, then we use this formula. We get our Z value of the critical value at Z alpha over 2 and Z alpha over 2 and multiply by sigma over root of n, where our sigma is our population standard deviation. So how can we get the standard deviation from the population variance? We just square it, right? So that's the formula that we use. Okay, so the next slide. Yeah, so I think we'll, okay. So we got to our example. So in okay. So before the example, we just have The confidence interval again is written like that. So we can say that Z alpha over 2 multiplied by sigma over root of n is just known as the margin of error. So yeah, so that's the margin of error. Okay, we can read that, I think, on our own. The population standard deviation can be reduced. I mean, the margin of error is reduced if the population standard deviation goes down, or if the sample size is large. Okay, so SNAT is asking, what if the population variance is not normally distributed? Now, SNAT, to start with, your question is wrong. We're not talking about the population variance being normally distributed. We're talking about the distribution of the population, okay, to start with. So, if the population variance is known, which is our first case, if the population variance is known and our population distribution is known to be normal, then we use the Z distribution. Okay. Now, if the population variance is still known, but our variance, our population distribution is unknown, okay, then we check the sample size. If it's greater than 30, then we assume that the distribution of the population is normal. If it is less than 30, then we cannot say that the distribution is normal, okay, unless we are told. So that's my answer. I hope you've gotten something. Okay, so that was on the margin of error. We can also increase the level of when we decrease the level of significance, then we can reduce the margin of error. Okay. Now, if our Z value, we have a 95% confidence, what will be the Z alpha over 2? It will be 1.96. Okay. So you get this from your table. I hope you can at this moment. Is there anyone who can't obtain the Z value given the level of significance or the confidence level? Is there anyone who can't get this 1.96 from the table? I'm asking, is there anyone who can't obtain the 1.96 from the table, from the standard normal distribution table? And there's silence. You can type as well. Okay, so let's start with the first one. Okay, let's start with the 90%. How do we get that from our table? 90%. How do we get that from, for 90%, we have the Z alpha over 2 is 1.645. How do we obtain that from our tables? You can just explain. You can tell me as well if you don't know, so that we go through it together.
Madam, can you please go through it together?
I want to hear the I don't know first. Why are you just asking me to go through it with you?
I don't know, madam. Thank you.
You guys are clever. I don't know. It's now IDK. Okay. It's a clever way of saying it. Okay, so let me just let us share a screen so that I take you to the table. I hope you have your tables. Okay, I'm trying to share a screen with you. Okay. There's noise in the background. Okay, so we start with 90%. So at 90%, what is our alpha? What is our alpha? At 90%. So can you see that screen? Or maybe I make the values bigger. Okay, I've asked the question, what is our alpha at 90%? Because that is the starting point. Okay, 0.1. Okay, cool. So our alpha is 0.1. Now, our alpha is 0.1. But remember, we're saying that our alpha should be, it's a Z alpha over 2, right? So divide alpha by 2. We get 0.1 divided by 2. We get 0.05, right?
Yes.
Okay, so we get 0.05. Now, remember that we are looking for just bring this. Okay, now we remember from the normal table, the area under the normal table is given by the probability, right? Now, the 0.05 that we have found, I see, 0.05 is actually the area that is in white here, okay? But we are looking for the probability of Z less than or equal to that value, the value at which we have this probability. So we're looking for the small z. So what we do is we subtract that 0.05 from 1. Remember, total probability is 1. So if we're going to subtract this 0.05, then we're going to find this probability, which is the shaded region. So then subtract that from 1. So that is 1 minus 0, 1 minus answer. You get a 0.95. So 0.95 means it's the probability for this region. So we go on our table and look for 0.95 in our table. So 0.95. So it's supposed to be somewhere. Okay, so 0.95, you see. I think we have to make it smaller. Okay. Okay. Okay, so 0.95. Just look in your table. You just have 0.9495 and 0.9505. We can see that, right? Can we see 0.9495 and 0.9505? Can we? Are we together? We're looking for 0.95 in the table, inside the table. But we don't have an exact value. We just have 0.9459 and 0.9505. So can we see those two values? Okay, you guys are quiet. I need some responses. Can we see those values?
Yes, we can.
Okay. Now, since we don't have an exact, what do we notice? If we add those two and divide by 2, we have a 0.95. Just try to add 0.9495 plus, and 0.9505. Add those and divide by 2. You find that you have 0.95, which is the probability that we are looking for. So that means that the value is right in the middle of these two values, right? Okay, so now we follow the Z values for these two numbers. So that is 1.64, right? And 1.65. Those are the Z values, right?
1.64, 1.65. Yes.
Yes. So we add those as well and divide by 2. So that gives us how? 1.69. Where are you finding this 1.69? Then I don't know what NP means. I don't know if it's a NOP or... Okay, so we'll go through it again. Sanga, the 0.829889. How did you get that? Then Margaret, I don't know what the NP means. Don't know if it's a NOP or... Yeah. Okay, so for those that are following, at 1.64 and 1.65, we have two values which add up. And when you divide by 2, you have the probability that we are looking for. So similarly, we get those two Z values, add them and divide by 2. Okay. We'll go through this again. But for those that we're following, that is how we have our 1.645. Because when you add and divide by 2, then you have 1.645. Okay. Okay, so let's go through this again. We're looking for the Z value. Okay. We're looking for the Z value that is the critical value for a 90% confidence interval and how to get that on a Z table. Okay, but you are lucky that your table will give you the values. Okay. Okay. Okay, let's start all over again. Okay, so we're talking about maybe I should be typing. We first divide alpha by 2. So we all agree that 90% confidence interval, our alpha is 0.1, right? At 90%. Then we divide by 2. Divide alpha by 2. After dividing by 2, subtract the answer from 1. There's some noise in the background. There's some noise. Then okay, there's some noise in the background and I can't see who. Oh, okay. Let me just mute. Just follow the steps. I'm typing the steps. Then you subtract your answer from 1. And then look for
go to another slide. When you are connected to the inner site, which has been given.
Look for the probability in the table and get the critical values or the Z values.
Madam,
Yes?
can we try 1 minus AZ? AZ in this case being 0.95, and then we find that's the answer for alpha over 2. Then, for instance, what I'm saying is Z is 1.645, and then AZ is 0.95. So if 1 minus AZ is 0.05.
Okay, you're kind of breaking. Okay, you're kind of breaking. Okay, now I can get you. Yes?
Yes. I'm asking
you
if
can
you
go
can
on.
try to finding the confidence interval. We say 1 minus AZ from the table, just on top there, on the right-hand side of the graph.
Yeah.
So Z in that case
and what will
is
be
1.645, and then 1 minus AZ would be 0.05. If we multiply that by 2, can that give us our A, being the 90% confidence? Because I've seen it's saying that's the lower limit of the right 5% tail. So because we're using alpha over 2 is the left lower limit and the right limit. So is it safe to say that, okay, that side, if we multiply that by 2, that means we're at a 90% confidence?
Okay, the problem is that you're kind of breaking. Maybe you can.
Let me try typing it.
I don't know if others can get you. I'm not, but I think I've got an idea of what you're saying. You're saying we should just use the table on the right? Okay, now I can't get what you're saying, like completely. Okay, so the table on the right is a summary. Okay, let me just explain on this. The table on the right is a summary that you can use. But first, I didn't want you to just get to be using the table on the right, because you might find a table without this summary. And you might be given a percentage like 85%, which is not amongst the common percentages, and you'd be stuck. So that's why I'm telling you, showing you how to do it for any percentage. But for the table in the right, here it's telling us that the lower limit of right for a 5% tail, a 5% tail is just when alpha is 0.05. So when alpha is 0.05, when alpha is 0.05, then our Z value will be 1.645. Now, you're looking for, in our confidence intervals, we look for Z alpha over 2. Okay, so if our alpha is 0.1, divide that by 2, you have a 0.05. That means you have a 5%, and you can get your Z to be 1.645 from that table. If we're looking for a 95% interval, our alpha is 0.05. But we then look for the Z alpha over 2. So you get your 0.05 divided by 2, you have a 0.025. Then multiply that by 100, that is a 2.5%.
Yeah. It's wild.
Okay. Okay, yeah, there's some noise again in the background. Okay, so for a 2.5% tail, then your Z value, the critical value is 1.960. So you can get their Z values from that table, the summary table on your right. Okay, now we're going to go back to the table. We're going to go back to the normal table. I'm having people are asking if we can go through how to obtain the Z values. Okay. Okay, so for a 90% confidence interval, our alpha was 0.1. Divide that 0.1 by 2, you have a 0.05. Subtract 0.05 from 1, you have a 0.95. Look for the 95 in the table, and you find that it is between 1.64 and 1.65.
Maybe for now, it's better to concentrate on what we have.
Okay, so that is the 1.64. So you find you're looking for 0.95. So it is between 1.6495 and 0.9495 and 0.9505. So you get an average of those numbers and you find 1.645. So that is how you find the value. And for a 95%, let's go to a 95%. Our alpha is 95%, our alpha is 0.05. Divide that by 2, you have 0.025. Subtract your answer from 1, you have 0.975. Now look for 0.975 in the table. 0.975. So we look for that 0.975. 0.975. So it's right there. So we're looking for 0.975. So can we see 0.975 in the table? Can we see 0.975 in the table?
To how the connectivity.
Okay, can we see 0.975 in the table? Can we? We're looking for 0.975. Can we see it in the table?
Yes.
Yes, madam.
Yes, you can. Okay. So if you can see the 0.975, it is right there. Now follow what the Z value would be for that probability. What is the Z value going to be for that probability? The 0.975. Okay, now we're looking for, if you can see it, okay? Now we're looking for the Z value.
1.9.
1.9, 9 what?
6. 1.96.
Yes. So we have that 1.96. And that is how they got that 1.96 in the summary box. Can you see it there? 1.96 for 0.975. Okay, we've seen it, right?
Yes.
Yes, madam.
So this is how we get our values. And let's look for a 98% confidence level. What is our alpha going to be for 98%? 98%, what is our alpha going to be? %98 confidence level, what is our alpha going to be? Okay, you guys, I'm waiting for the answers. 98%? Okay, 90. Okay, so 0.02. Then what's the next step? 0.02, we divide by 2, right? Because we are looking for Z alpha over 2, isn't it? Okay, 0.02. So we divide that 0.02 by 2. 0.02 divided by 2, okay. 0.01, right? Okay, now subtract this 0.01 from 1. So you say 1, 0.99. So that is the probability that we'll look for in the table. 0.99. So take note, we're looking for 0.99. 0.99. Okay, can we see it? 0.99. Okay, so can we see 0.99 from our table?
Yes.
But in this case, we don't have a 0.99 as in just the way it is, right?
Yes.
So 0.99. Okay, so we have 0.9901 is the closest, right?
Yes.
Yes.
So now so take note of that, and then we check the Z values, the critical values that are corresponding to that probability, 0.9901. So what will our Z values be? Okay, is it too small? What will our Z values be for 0.901? I mean 9901.
2.3.
2.33. 2.33.
Yes. 2.33. Okay. And again, when you look to that summary corner, okay. Okay, so they've said 2.326, but we usually just round it off to 2.33. As you can see, that 2.326 can still be rounded off to 2.33. Okay, so that is how they've obtained that value. So from here, you should be able to find the Z values for any confidence level. Now, today we have just done this, and we're supposed to be done with this. Just been reading the table. Okay, so let's get back to our slides now. Yeah. Emmanuel, how did you get this 2.326? Because all of us have found 2.33. So, okay, from our slides, again, we can see that at 98, we have 2.33. So try out all these other percentages and see if you can get those. You can get those Z values. Okay. So remember, we're still constructing our confidence interval for the mean when the population variance is known. The distribution again is known, and is said to be normal. Okay, so this just explains that for any confidence interval, we'll have a percentage that falls within that range, and some interval may not fall within the range, so we cannot be 100% sure. Okay, so we are going to the next slide. Okay, there's our example. A sample of 11 circuits from a large population has a mean resistance of 2.2 ohms. We know from past testing that the population standard deviation is 0.35. So our N is 11, right? From a large normal population. So we have been told that the population is normal, right? So we just take our N, the mean resistance, this is the sample mean, is 2.2, and we are told that the standard deviation, the population standard deviation is what? 0.3. 0.35. So we then construct our confidence interval. Okay, so have we been given the level of the confidence level? Have we been given the confidence level? Have we been given the confidence level in this question?
Yes, madam.
Where is the confidence level?
Right.
Or what is
95%.
95%.
Oh, I just didn't see it.
The question.
Okay. Okay, so we're told to use to create a 95% confidence level. But in a case when you're not given the confidence level, if you're not given, you use a 95%. Okay. So that is how we construct our confidence level. Now we know that for Z alpha over 2 at 95%, we have 1.96. Then you just replace that over our N and you add. So this is our confidence level. You can either write the two numbers and you just put brackets. You say you open bracket 1.9932, comma 2.4068 and you close brackets. That's still a way of presenting a confidence interval. Okay. So should be winding up now, and okay, the slides are taking quite some time. So in the next slide, we have using we have a second case when the sample size is when the the population variance is unknown. Okay, I think you also have to note that we give a description of the confidence interval. So we say we are confident, we are 95% confident that the true mean lies between the range that you have. So you use we are 95% confident. Don't say I am confident. I will find in those answers in the mid. I am confident. No, you don't use that. You say we are confident. Okay, so for the confidence interval, when the population variance is unknown, we use the t distribution instead of the normal. Okay, so in that same formula, we substitute the standard deviation with the sample standard deviation. Okay. Okay, so we go to the next slide. So that is the formula. So this is the student t distribution, or you just say t distribution table. Now for the t distribution table, I think we have seen in the table before. You have the probabilities as the columns, and inside the table, you have the t values. Okay, so let's see from an example. Okay. Okay, so that's just a summary. Okay, so there's one thing that we have to take note, the degrees of freedom when we're using the distribution, very important, obtained from subtracting 1 from the sample size. Okay, so we're going to the next slide. Okay, so when n is 5, what are the degrees of freedom? When n is 5, when n is 5, what's the degrees? What are the degrees of freedom?
4.
4, okay. Yeah. So the degrees of freedom will be 4. Okay, so we'll see from an example how to read. Okay, I see you posted the answer. So let's just go to the next slide. Okay, there's a video that I uploaded on how to read the t-table. Did you guys listen to that? The video on how to read the t-table. Okay, so we have okay, so we have the t-table there. This is how it looks. So we have degrees of freedom, and they go on up to somewhere 50. And then on top there, the columns, you have the probabilities. So for t, if alpha is, if n is 2 and alpha is 0.1, remember we always say it's supposed to be t of alpha over 2, comma, the degrees of freedom. So if alpha is 0.1, then we look for alpha over 2, which is a 0.05. Then t n comma 0. T 2 comma 0.05. It means the top column will have a 0.05, and on the degrees of freedom will have 2. Where they meet, that is your t value. So that's how you obtain your t value. So we see now from our example. Okay, I've clicked on the next slide. So our t values just tend to be normal. Okay, we'll go to our example now. It's taking time to.
Well, many things happening now.
So our example reads, a random sample of n is equal to 25 has a mean of 50 and a sample standard deviation of 8. Form a 95% confidence interval for the population mean. Okay, so that is our example. I'm sure you have it since you have the slides.
Other things for now, maybe
okay, so in that example, our n is 25, our mean is, sample mean is 50. Our sample standard deviation is 8. And we're asked to form a 95% confidence interval. So for a 95%, what is our alpha? Alpha, we have already seen that our alpha will be 0.05, right? 1 minus 0.05. So our alpha is 0.05. Now alpha over 2. Oh, okay, the slide is here. So our alpha is 0.05. Now we're looking for t n minus 1 comma alpha over 2. N minus 1, our n is 25, so n minus 1 will be 24. Alpha over 2 will be 0.025. Then we look for that value. So we go again on our table, our t table. Okay, can you see the screen now? Okay, we're supposed to be sharing a screen. Supposed to be sharing a screen. Okay. Okay, so okay, let me just make the table bigger. So our alpha is 0.02, I mean 0.025. Just have to make it smaller. Okay, so our alpha is 0.025 and our degrees of freedom is 24. So we follow that rule for, Okay. Okay, so our alpha is 0.025 and our degrees of freedom is, okay, let me just do the screen sharing again. So this is the last thing. This is our last slide actually. Okay, it's taking quite some time, but you just go to 0.025 and you follow the row of 24. So in that row, under the column of 0.025, you find that your answer will be 2.026. Put that in your formula and then complete the calculations. So that's how we get the confidence interval. Okay, so tomorrow. So tomorrow from 14 to 16, should be able to wind up on this, and we'll begin confidence intervals for proportions and population variance. Okay, so we'll end here. Any questions?
We try and action the procedure through which the exam is being done. So make the initial
Any questions?
looked at could be shared all of us.
Madam,
And the
Mm-hmm.
there are issues from here which you need
is this video also going to be posted? I don't know, on the Moodle app.
to
Yes. So by tomorrow you should be able to go through, and it can even be downloaded.
Okay, so the only place it can be downloaded from is from the Moodle app.
Yes. So by tomorrow, it will be ready tomorrow. Click on the name of the presentation, which is estimation.
Estimation.
After you click on that, after you click on estimation, it will open up. Then click on presentation.
Okay.
After presentation, it will open another window and it will start playing. Now, there are some 4 arrows that you can see beside the presentation, or the 4 arrows that can make the presentation to be on full screen. Can you see those 4 arrows on the right corner? Can you? Can you see the 4 arrows? So those 4 arrows, when you click on the recorded presentation, you click on those 4 arrows, you just see the people that were logged in using the video, and you click on that video, on the presentation that is playing, then you can save the recording. So that's how you download it. But I'll still download it for you guys and give you a link.
All right.
Okay, thank you so much. Hope you got something.
Madam,
Yes.
Yes.
I have a question.
Ah.
How are you finding these the critical intervals?
But
The
we're going
2.5. Yes, my network was bad, so I couldn't get you clearly.
Okay. Okay, so what you do is that maybe just wait for the presentation tomorrow, because I've got a class at it has actually started, and I'm 4 minutes late. The distance students. Yeah. So, but I can still check on me on my WhatsApp. I'll reply to you. Yeah.
Okay, thank you.
All right. You can ask your friends. I'm sure some got how we got those answers.
Okay.
Okay. All right. Thank you, guys.
Thank you.
Okay, have a good day.
Thank you, Sam.